Okay, let's summarize our requirement for a driver for unipolar stepper motor as we learned yesterday in a previous lecture. Okay, so the first requirement is that let's say you need to decouple supply voltage V from on current phase. This makes possible to increase the voltage, and in that situation we can have fast turn on. Okay, this is done for, say, to get faster turn on, and this is obtained by adding a current control. Okay, you need to control the current flow into the phase, and then you act on the switch in the driver in order to, let's say, not wait for the wall transient to be ended. This is the first requirement. The second requirement is that the driver, it is asked to generate a large negative voltage across the phase of the stepper motor to get, say, faster turn off phase. And these are the basic two main requirements that we need to implement for a more efficient driver, in the sense that you can use very large pulse per second input, so you can operate the stepper motor for a very large and high frequency. There is a third requirement that is always present. This is already obtained even in the previous L over R or R over L driver, that the driver must generate a, let's say, unidirectional current. Okay, we are talking about unidirectional stepper motor, so the current must flow always in the same direction through the phase. Okay, these are the requirements. So let's introduce a circuit that will be, say, employed in driving the unipolar stepper motor, and that maybe can say, add the requirements I listed before. Let me draw this circuit, then we analyze it. Okay, so the V is the power supply providing to the phase. Then let's have here a switch that can be, say, a MOSFET or an IGBT. Let me put there just the symbol for a generic switch. Let me call this switch like TA plus. And then we have another switch, which is TB minus. LA and RA model the stepper motor phase. For example, this is the phase A. Of course, this circuit needs to be replicated for other phases. This switch is called DB plus, and this is DA minus. Later on in this course, it will become clear how I give this specific name for all these components, okay? A plus, B minus, B plus, etc. So the circuit now is a little bit more complicated than the L over R or R over L circuits that we studied before. Just say see how the circuit can be operated. Okay, so let's consider the different combination of the two switches. Okay, and see what happens. Consider the situation in which TA plus and TB minus are both on. So they act as a closed switch. Okay, so let me just do see what happens. Okay, if I have these two switches that are closed in this way, what happens to the diodes DB plus? DB plus has the cathode, which is connected to the positive polarity of the batteries, and the anode, which is connected through TB minus to the reference voltage. So the voltage V is totally applied across the diode, reverse biasing the diode. So DB plus is off. Okay. And what happens to DA minus? The same, because the anode is fixed to 0 volt, while the cathode through TA plus, which is conducting, is connected to V. So DB plus, but also DA minus is off. So in that situation, which is the resultant circuit is the well-known circuit that we employ to energize the stepper motor winding. Okay, the voltage which is applied to the phase is exactly the supply voltage V. So this is the circuits that we can use for the turn on. Which is a difference from previous, let's say, analysis. Basically, there is no difference. Okay, you applied V, and then you have to consider which is the evolution of the current flow into the phase IA over T. The difference now, if you want, is that the current flowing through the phase is measured, okay, by a sensor, and exactly at the time instant in which the current reaches the maximum permissible current flowing through the phase, then the switch TA plus or TB minus are commanded to modify their status. And so this means that I have not to wait for the current to reach the V over RA maximum possible current for the circuits. Okay, so in that we'll see an example later, but this turn on is always, let's say, obtained by using the same circuit as before, plus some current control action in order to decouple the voltage V with the maximum V over RA current flowing through the phase. Okay, we'll see an example later on. Now, what happens, for example, if I have this is the first case, okay, which is the turn on. The second possible combination of the switch is that having, let's start with TA plus on and TB minus off. So in that case, we have okay, Tb minus is open. Okay, in that situation, we'll see that dA minus is off, okay, for the same reason that we say have in the step number 1, okay, the diode as the cathode and the anode in parallel with the voltage V. So in that case, dA minus is off. What happens to dB plus? So in that situation, I have a current, okay, here, flowing through the phase, and this current flowing through the phase cannot be flow from, say, the positive plus to ground here, because dB minus is open. So the only possible, say, path through which this current, so the current through the phase can flow is through the diode dB plus. Okay, so the diode dB plus is on to free wheel the phase current. In this case, which is the voltage that you have in the circuit, if you want, is this one. dA plus is on, then you have LA, RA, and then you have the diode here, dB plus. The voltage that you can have across the phase, VA, is something like minus VF. So it is negative. It's not so large because it's the small voltage drop across the on diode. So let's say 1 volt, 1.5 volt. But it's enough for, say, making a turn off. So here the current through the phase is decreasing. The IA over the T is, say, negative. So meaning that you have, say, a reduction of the current. So it's not so large, but it is negative. So it, say, something that you can use for, say, turn off. Let me see what happens in a different phase, which we can call third phase, in which TB minus now is on and TA plus is off. So this is exactly the situation which is opposite to the previous one, okay? So TA plus, sorry, is open, and TB minus is on. So what happens here? As you can see, dB plus now is connected in parallel to the voltage V, reverse biasing it. So dB plus is off. What about dA minus? But if you have a current flowing, say, in the phase, the current IA, this current cannot flow anymore when the TA plus is, say, turned off, because you are interrupting this current. So the only path that this current finds to continue to flow is through the diode dA minus. So dA minus is on because it is useful for freewheeling the current in the phase. Phase current, which is the equivalent circuits that you can have in this situation, something like this. LA, RA, and then you have dA minus. Okay, so the voltage VA across the phase, again, is the small voltage drop across the on diode dA minus, which is on. Okay, so in the same way we analyzed before, the current flowing through the phase is negative because you are applying a negative voltage across the phase. And so this is a situation that you can use for, let's say, reducing the current and turn off your phase. But look at what happens when you have another phase, okay, which is the situation that is obtained by using Ta plus and Tb minus both off. Now, even the circuits here is Tb minus is open. So both the transistors are open, and if you have this configuration of the switches, the current through the phase cannot, say, continue to circulate. Again, you have a situation in which you are forcing the interruption of the current flowing through an inductance, okay? In this case, the inductance LA modeling, say, the inductance of the winding. And so this is not possible. The current, say, forces the conduction, tries to continue to flow. And since both the switches are off, the only way to continue to flow is to have this recirculation path. This means that when both transistors A plus and B minus are off, the diodes Ta minus and Tb plus are on. So what happens in that situation, which is the equivalent circuits that you have? The equivalent circuit is something like this. You have V, which is the external power supply. Let me call these two nodes are, say, A and B. Okay, the two ends of the phase winding as A and B. So you have from the positive polarity, you have the diode, which we can assume to be a short circuit. Then you can have the node B. Okay, and then from the node B, you have array, node A, and ground. So which is now the voltage VA. The voltage VA is the voltage that has the positive polarity, say, concordant to the node A. So VA here is this voltage. Okay, as you can see here, the voltage VA is minus V. Now the voltage that we are applying this specific combination of the switch status is exactly minus the external power supply. And this is negative, so it means that you can employ it for, say, obtaining a reduction of the current, so the turn off of the phase, the energization of the phase. But this is large because V can be made, it's a very large, because at the beginning of our discussion, I said that we are able, controlling the current flowing through the phase, to decouple the magnitude of the admissible voltage with respect to the maximum current flowing through the phase. So V can be made large without any, say, penalties in terms of turn on. And so that means that in that situation, the voltage V, which is very large, can employ to get a very fast turn off. Okay. So this circuits provides all the requirements that I listed, say, in the previous page of this class. Okay, This first part is obtained by a specific current control, which is not shown in my explanation. Okay, something that acts on the switch when a specific maximum permissible current is reached in the phase. Okay, I have not to wait all the transient to finish. Then it is able to generate a large negative voltage in order to get faster turn off, because I show you that you can have the turn off phase, which is driven by a negative supply voltage minus negative V, okay, which is symmetrical to the turn on, in which the voltage VA is plus V. Unidirectional current is, say, what you get always in this situation. The current always flow from, let's say, the node A to the node B. In all these combinations of the switch, the current is always, let's say, having the same direction. So it is unidirectional. Basically, this circuit is a circuit that, exploiting these 2 points here, provides a unidirectional current, so always from A to B, and as, say, reversible voltage. Across the phase, because the voltage VA across the phase can be positive, plus V, or negative, minus VF or minus V. So this is a situation which our driver is a, let's call, 2-quadrant driver, okay? Because if you look at a plane in which you have, for example, the voltage VA, which is the voltage across the phase, and the current IA flowing through the phase, that you can have operation in these 2 quadrants here. Okay, the voltage can be, say, positive or negative depending on the status of the switch, and the current is always unidirectional. Okay, so this is a 2-quadrant converter. This circuit is, say, let me just answer the question. I have a question from Antonio Moles. So with this circuit, the best combination to turn on off is to drive simultaneously on and off the MOSFET. Now I'm going to, let's say, analyze in detail which is the best sequence of the switches. Okay, I have to say that in order to get faster turn off, of course, you have to employ the, say, maximum possible negative voltage applied to the phase. So this means that for the turn off, the best situation to have both the switches, say, off, say, open. And for the turn on, for sure, you have, let's say, the best situation, which is having both the switch on. Okay, so, but something is, say, to be discussed when I want to maintain constant the current. Okay, so for the turn on and the turn off, you are right. Okay, both the switch on, turn on, both the switch off, turn off. Okay, that are very fast. But this is not enough. We have to understand what happens when I want to maintain, let's say, the phase energized. Okay, not just off and on phase, but just when you have the phase on. Okay, but this is just, let's say, a matter of few minutes. Okay. Marco Simonetti asks, are the second and third equal in terms of speed to turn off? The second and third are the situation in which you have, let's say, the voltage VA, which is negative and equal to the forward voltage of the diode. Okay, of course, this means that since they have the same negative voltage applied to the phase, the speed is basically the same. Okay, this is right. Okay, so this is an example of 2-quadrant converter. Means that you can, say, employ to have, say, reversible voltage. Means that the voltage can be positive or negative, and unidirectional current. We'll see in the rest of the course that will be, say, other kind of 2-quadrant converters. Then we learn the existence of 4-quadrant converter. So this is just the first example. Let's try to, let's say, examinate a little bit what I'm saying before. So what happens for a practical case? Okay, so let me just do this kind of explanation by performing an exercise, so that I understanding a simple, very simple exercise. Okay, so let me consider this example. The example is the following one. I have my phase, which can be described looking at the datasheet by these parameters. LA is 50 millihenry. Losses RA is 10 ohm. The voltage V applied from the external side to supply the phase is 340 volt. Let me just put here the typical waveform for the current through the phase that always you can get employing this specific circuit. By the way, these circuits can be considered as which is a two-quadrant converter. Sometimes is also called chopper driver for unipolar stepper motor. Okay, so the standard, say, behavior and waveform for the current flow into the phase for this chopper drive is typically something like this. Remember that I said that the manufacturers specify a maximum possible current, maximum permissible current, in order to avoid heating up of your phase, that you avoid permanent failures. And then manufacturers also specified a minimum current to get the required torque from your output shaft of the motor. Okay, so let me put these two, say, limits, these bounds, having this value 5 amp and 10 amp. Maybe this let's say band is somewhat exaggerated just to better show what happens. Okay, typically this is not say something that you can easily see in your data sheet, or maybe something that you cannot tolerate, just this large difference from the minimum to the maximum admissible current. But anyway, just to show what happens. The typical expression for the current flowing in the phase for a chopper drive is something like this. Let's say start with the turn on. The turn on is interrupted here. And what does it mean is interrupted here? That there is a, say, current sensor providing information that, okay, your phase current is approaching 10 amp, which is your maximum admissible current. So change the status configuration because you already reach your maximum current. Okay, so the voltage here is chosen to get that specific turn on time interval. Okay, but when the current in the phase approaches 10 amp, which is the maximum, then the configuration of the switch will be changed. Then what happens here, in order to, say, operate, is that you have to apply something that that decreases this current from the maximum possible level. Okay, and then you can have a behavior like this. Then again, something which is basically the same current sensor I employed before informs you that the minimum current is approaching, and then something you have to change in order to, say, maintain the required, say, current level for your, say, correct operation. Okay, so here the current must, let's say, increase. and this variation, say, continues for the required time interval in which you have to maintain, let's say, your, say, current to be on. Okay, so you can say that this is something that can goes, say, for several periods in this way, and then you have your turn off. As I said before, the best solution for the turn off would be to open both the switches, okay, in order to get this faster transit. But basically, the behavior is like an, let's say, having an hysteresis in the current, and to maintain the current between the hysteresis band of this current, okay, making current goes down when it reaches the maximum admissible level, and to, let's say, rise up when the current is descending to values that are lower than the minimum admissible current. Okay, this is what happens. As I said before, this hysteresis band is somewhat exaggerated. Sometimes this kind of ripple is not tolerated, because if this range is large, as in this example maybe, then you can have a variation of the torque during this phase. Okay, during this, say, interval, you can have a variation of the torque. There is a ripple in the current, and typically this is reflected in a ripple in the torque. Okay, so also the torque is not constant due to the fact that your current is not perfectly constant. Okay, sometimes this can be tolerated. For example, if you have a motor, and this is valid for all kinds of motors. If you have a motor that has a very large inertia, the ripple in the current is not immediately, let's say, impacting the variation of the torque due to this large inertia. Okay, and so even if you have a very large ripple, like for example this case, then the ripple in the torque is minimized. But in other situation in which the inertia of the motor is, let's say, not so large, then you can have an immediate impact of a current ripple in the ripple in the torque. And this sometimes cannot be tolerated. So this kind of solution that, say, drive the motors in having this hysteresis in the current is not, say, tolerated, or maybe this band should be minimized. Okay, but anyway, there are solutions to, say, get rid of this ripple. We'll see a solution later on this explanation. Okay, so this is what we can have as a typical situation for this chopper driver. I want to use this data here to understand what happens for using different strategies for the section of the current which you have decreasing of the current. Okay, what happens here, what happens here, and what happened here? So these three interval, okay, this the interval here, which you have the current decreasing, because as I said before, while you have just one possible solution for increasing the current, and this means that I have here TA plus and TB minus on. Okay, this is the only possible way to make a current in the phase to be rise up. Okay, you can have, and so you can have a different solution for making the current decreasing. Okay, you can have, let's say, TA plus off and TB minus on, and then you can have TA plus and TB minus both off. Okay, for sure this solution will be employed here, okay, because it makes faster. But what happens inside this hysteresis band? So compare, and this is the question, compare different strategies for phase current reduction. Okay, so let's see what happened using different strategies. Okay, and see what happens, because maybe the strategies is not so obvious as it can be, say, appear at the first sight. Okay, so let's start, for example, just considering what happens for the first interval. Okay, let me call this interval here, okay, t1. Okay, just say see what is this time interval t1. This t1 has not possible, say, alternatives. In t1 you have to consider ta plus and tb minus both on. Okay, so this can be done in one step. Ta plus, tb minus, both on. Remember, this is something that we already studied, is the exponential variation. I have to understand which is the time interval between two different points. I provide you an expression that is something like this. I have 2 points, which are C and D, and then this is XC, XD, and the expression is simply that this delta T, so TD minus TC, is tau natural logarithm of x infinite minus xc, x infinite minus xd. Okay, so which is tau in our circuit is LA over RA, so this is 5 millisecond. It's 5 millisecond. Let me just replace this delta t with our t1. Okay, t1 is so 5 milliseconds natural logarithm of what? Which is the voltage that you can have at infinite. Okay, because now we are, sorry, the current we have to infinite. The current is VIA over RA. Okay, if we have TA plus and TB minus to be on, we have this specific circuit here. And so if you wait for the transient to be ended, the current that flows at the end will be exactly V over RA, as usual, as already they studied for previous driver circuits. And which is the current at the beginning is null, because our point XC is exactly this point here. VA over RA, then we need the point D. The point D is this one, and so it is the point in which you have your 10 amp. Let me say I final current. Okay, this is the I final, and this can be the I initial current. Okay, 5 amp and 10 amp. Okay, so this is what happens for T1. So T1 is 5 milliseconds natural logarithm of V. It's V, is not VA, sorry. It's V, just simple. V divided V minus RA I final. Check my results. I think that this is, let's say, 71.74 millisecond. Okay. T1. So the turn on. Okay. As you can see here, I'm not waiting for, say, the transient to be ended. Okay. After 1.74 milliseconds, I reaches the final current, so the maximum admissible current, and my action stops. Okay, so that means that I have to change the switch configuration. Let me just to see what is this time interval here. Okay, because T1 and T3 have no alternatives in the action. Okay, so we can use the same TA plus and TB minus to get this rising up situation. So T3 is simply given by the time interval that is needed for the current from the initial value 5 amp to reach the final value 10 amp. Okay, so let me just to finish this part computing T3, which is again 5 milliseconds, natural logarithm of what? The initial current is, we need to have x infinite, but x infinite is always, say, V over Ra. Now the initial current is the first point that we need to consider. And then you have infinite current, V over array minus final current. So this is 5 milliseconds multiplied natural logarithm of V minus Ra initial divided V minus array final. So it is 5 milliseconds natural logarithm of 340 volt minus 10 multiplied 5 amp divided 340 minus 10 ohm multiplied 10 amp. If I computed correctly, this is 0.946 milliseconds. Okay, so we just say computed the rising part of our T1 and T3 current wave. Okay, of course, also this part here has the same duration, 0.946 millisecond, etc., etc. Now the situation which is more interesting in when you have, say, different strategies, and this happens anytime you have the current that must, say, decrease. Okay, here and also here if you want. So let's just compute the time interval that I can call T2, okay, here. And this is T4, which is the turn off time. Okay, so let's start with T2. So this is just for, say, for the rising current. This is the turn on delay. So see what happens for the descending current. Let's say T2 can be obtained in two different ways. Okay, so let me just discuss what happened when you have, for example, the situation, let's say one of the two, in which you have TA plus off and TB minus on. Okay, in that situation, my circuit is is the number 3, okay, this one, Ta plus off and Tb minus on, for example. The equivalent circuit is this one now. The voltage drop is the modest negative voltage Vf, okay, because now we have the freewheeling diode Da minus, which is on. And so in that situation, we can compute Ta, say, for this kind of solution, say, switching strategies. The same time interval duration will be obtained if I use the, say, step number, the configuration number 2, in which Ta plus is on and Tb minus is off, because they lead to the same configuration. Okay, so I just computed just for this combination, but the situation is the same for the other one. Let me just to consider, say, our exponential, say, variation. Let's say this one. I have these 2 points. Remember that if you want to compute the delta t, which is this interval here, now this is tau natural logarithm of xa, so the upper point, x infinite, xb, x infinite. Okay, so I'm using now this expression to compute this interval. T2 now is, let's say, tau natural logarithm of what? Xa is the current that you can have at the beginning of my descending phase, so it is final current. And then you have the final current in my circuit. The final current in this circuit is something like, let's say, as the current goes into, let me put, just to simplify this computation, that my Vf is very small to be, let's say, neglected. So suppose that my diode is ideal. Okay, what does it mean? That when the diode is off, it is a perfect open circuit, and that situation is always reasonable. And when the diode is on, I can neglect a small voltage drop. Okay, this is something that I can do this in this circuit because my voltage V is 340. So even if you have a 1 or 2 volt for Vf, they can be negligible with respect to the other voltage in the circuit. So my hypothesis here is to neglect the voltage. Okay, so my current at the end of the circuits will be, at the end of the transient will be 0. And then you have the XB, and XB is the initial current, minus 0 gain. So this is 5 millisecond natural logarithm. If you want, this is nearly close to. Final current is 10 amp. Initial current is 5 amp. If I compute it well, this is 3.5 millisecond. Okay. The same happens if I change the combination of the switch, Ti plus on, Tb minus off, as I said before. But there is also another combination, and the other combination is when I put both the switch to be off. So the combination of the switch that I call number 4, if I remember well, here, exactly number 4. In the number 4 combination, when both transistors are off, the diodes are both on, and so you are applying a voltage across the phase, which is exactly negative V. So see what happens in that specific situation. Let me call this number T2 like T2 prime. Okay, is obtained when Ta plus off and Tb minus off here. and this is tau, natural logarithm of in this case we have that the initial current is the final current, 10 amp. Now, which is the voltage that you have at the end of the trans will be you can see here that let me just to share again these circuits. This one. At the end of the transient, the current flow into the circuits is only due to the resistance array because the in steady state situation, the inductance plays no role. Okay, and the current has this direction and is V over RA. The direction is entering the node B and exiting the node A. So in that situation, if you want, the current is a current flowing, say, reversing the direction. Okay, so according to my convention, is minus V over RA. So this is minus minus becomes plus. Then you have initial plus V over RA. Okay, if you have this expression computed, you have 5 milliseconds natural logarithm of V plus I final RA over V plus I initial RA, and this is 0.6 millisecond, more or less. As you can see here, there is a huge difference between this number here and this one. Okay, you have, let's say, 5 times lower and faster transition, but it is, say, completely understandable because you increase the negative voltage applied to the phase. Okay, so the T2 interval here can be made large or can be made very short, depending if you say employing the correct strategy for your phase. What happens to the interval T4? For the interval T4, just say employing the strategy that I showed you before here, the number 3, TA plus off and TB minus on, even if we already know that this is not, say, the correct way to have this turn-off phase, but just to give you, say, example, we have that we need the initial currents, which is our final current, I call I final. And I get 0 because I simplified the voltage drop of the diode to be 0. So let me just assume the same approximation as before, and which is the end current for my turn-off phase. So which is this term here to put here. The current will be 0. So here we have 0 minus 0, something like this. So this time is, let's say, infinite. Of course, this comes to be infinite because I neglected VF. Okay, so VF is not infinite, so you have a very large time, but anyway, you have to wait, so not an infinite time. Typically, if this is tau, we can see that the transient ends with a number of a time constant that can be from 4 to 7 tau. So let me just conclude that my T4 is in the part of 5 millisecond multiply 7, for example, 35 milliseconds, more or less. When you use T4 computed with both transistors off, which we already know to be the best solution for the turn-off, then you have tau natural logarithm of I final minus V over array, then 0 plus V over array. So tau natural logarithm of V plus 10 amp multiply 10 ohm over V. And this is 1 point, if I computed well, 29 milliseconds. Okay, so again, 1.29 versus, let's say, tenths of milliseconds. So, of course, this is to be preferred. So let me just to summarize our computation that I hope that are not, say, too much complicated, okay, and just see what happens in two different cases, okay, for the current flow into the phase A, in two different strategies. Let's say in the first one, using TA plus off and TB minus on for reducing the current. And here, always using TA plus off and TB minus off for reducing the phase current. So, two different strategies for, say, reducing the phase current. Nothing changed for what concerns the turn-on phase, okay? Because the turn-on phase in both the situations is always generated by putting TA plus and TB minus on. Okay, so here you have the time interval that is 1.74 millisecond. We have TA plus TB minus. They are on and they are on. This current level is 10 amp. Now the difference starts to appear exactly when you have the first part of the current that need to be reduced. Because in one case I have, let's say here, as very small transient, something like this. And this time interval is 0.6 millisecond, okay? In that situation, I have TA plus off and TB minus off, okay? What happens in the top case, in which I do not adopt the both switch off, it happens that I have something like this. This interval now is, if I remember well, let me just copy here, 3.5 millisecond. Okay, and here I have TA plus off and TB minus on. Okay, so nothing changed for the third variation of the current, in the sense that you have here a time interval which is 0.946 millisecond, and here you have something which is the same, okay, 0.946 millisecond. Then you can have several of this interval, okay, this way, etc., etc. At a certain point, you have the, let's say, suppose that from this point on, you command all these parts should be the same. And you command the turn off of your phase. The turn off can be obtained by, say, what I said before to be more or less 35 millisecond, not in scale here, or you should have the phase here, which is 1.29 millisecond. Okay, so this is say the comparison that we had for two different strategies adopted, okay, for say reducing the voltage. So it is quite evident that there is a huge benefit in turn off the phase using this specific say strategy here. So having TA plus and TB minus off. Okay, because in that situation you can see the current waveform has not this tail very long that say limits the increase in the pulse per second frequency. Okay, so you cannot act, cannot get your torque for very high frequency operation. So this is something that you have to say consider. So the strategies for the turn off will be, let's say, adopted always using the large negative voltage applied to the phase. Okay, this is evident in this phase. It seems to be also the same conclusion to consider even in the, say, on phase, which is this one. Okay, also in those phases you can say that, okay, but I can use the same strategies, both transistor off, for the, let's say, decreasing phase of the current here because it's faster. Just to consider what happens in terms of power dissipation, okay, in the switches. As you can see in my example here, the on phase, so the phase in which you are energizing your, say, your phase, in which you are having the current flow into the phase more or less constant in the hysteresis band, has the same direction, okay, which is this one, okay, T on, let's say, T on is here. Which is the main difference, that the frequency of the ripple in the current is very different, okay? Let me just you consider which is the frequency of the ripple in the case, let's say, in the top case and in the bottom case. Current ripple frequency. This is F 1 over, I call, if I remember, T2 and T3. No, see, yes, T2 and T3, this interval. The T2 and T3. Let me just to see. Yes, T2 and T3. So the frequency is 1 over T2 plus 1 over T3. And so you have two different results, depending if you are using the strategies of having TA plus off, TB minus on. This is 1 over T2 is 3.5 plus 0.9, etc. And this is more or less 225 Hertz. And this one is for TA plus and TB minus both off, in which this is 1 over T2 prime plus T3 prime. So it is 0.6 plus 0.9, etc. And this is 646 Hertz. So the frequency of the ripple in the phase current is, let's say, more or less, say, more than 2 times in the case you are using the strategies for the, say, reducing the current, which is TA plus TB minus off. And what is the impact in the power dissipation of transistors? When you switch on and off, say, switch, for example, a semiconductor switch like IGBT or MOSFETs, what happens is that you have a contribution of the whole power dissipated. That is called the switching dissipation, the dynamic dissipation. Or the dynamic dissipation that is always proportional to the frequency of switching. Okay, so what does it mean? That in the case you have an higher switching, then the power which is dissipated, the dynamic power dissipated just due to the fact that the switch is turned on and turned off is larger. Okay, but the situation is even worse because look at the sequence of the operation. Okay, so let me just to consider the top sequence. For example, you have this situation. For the turn on, you have TA plus on and TB minus on. Okay, this is the first turn on. Then you have the first phase in which you have TA minus off and TB minus on. Okay, that combination of the switch is say this one. Okay, I'm just putting in sequence the switch combination for this phase, and etc. So this is one for TA plus on, TB minus on, etc. in this way, and the last one will be again TA plus off, TB minus on. Okay, as you can see here, there is a switch that is always on. And then you have the switch TA plus that becomes on, etc. So you have just one switch that continuously commutates. Okay, in the situation that is due to the alternative strategy of commutation, you have something like this: TA plus on, TB minus on for the turn on, exactly as say in the previous situation. Then you have TA plus off and TB minus off for reducing the current, alternated to TA plus on, TB minus, say, on, etc. And then you have the final part, which is TA plus off, turn off phase, TB minus off. Now, the switch action is for both the transistor, say, continuously. See, here, on, off, on, off, on, off, and also for the B transistor. So here we have two transistor switching, and here just one transistor switching. So if you want this difference here, is to, let's say, you have to consider the fact that you have, let's say, 2 multiplied by 2, if you want to consider the dissipation, the overall dissipation. The overall dissipation here is due to the something which is proportional to F for 2 switches in the, say, configuration. Let's say, let me call this A and let B B. Okay, in the configuration B. And this switching frequency multiplied just for one switch for the configuration A. Okay, so if you want to consider which is the ratio of the power dissipation, you have to put 746 Hertz. This is for the B case, over 225 Hertz for the A case, and this is something which is close to 2.9. Okay, but then you have also considered that in the B case you have 2 switches, so the difference, the ratio of dynamic power dissipated by the driver is 2.9 multiplied by 2, okay, which is 5.8 times higher in B. So let me say that 6 times larger power dissipated for the configuration B, so this one, is something that typically is not tolerated, okay, in circuits that should have a very large efficiency. This is the reason why these 2, say, switch combinations are typically mixed up. Okay, so the situation is that you have for the part in which you have to increase the current, both transistors are on, and this is common for the 2 situations. For the situation which you have to turn off your phase, both transistors are off, because this is the fastest way to turn off your phase. But in between, when you have to consider the on phase for your, say, stepper motor, so we are inside this time interval, then it's preferable to have this switch combination. Okay, so having just one switch be on and off. So mixing up these 2 situations here, we can say that the best strategy is to have TA plus, TB minus both on at turn on. And then one of the 2 switching, TA plus off, TB minus on, TA plus on, TB minus on, etc. Here for the on duration, and having TA plus off and TB minus off for the turn off. Okay, so it means that the transistor TB is always, say, on from turn off, except for the case in which you have the turn off. And then TA plus is switching, say, alternating at the frequency. Okay, this is the situation that leads to have less dynamic, say, power dissipated by the switch, and you have the fastest turn off phase, possibly increasing the, say, torque for very large power pulse per second. Okay. Have you any questions? Okay, if you have no questions at all, we can have a 10 minutes break. Okay, so let me just to pause the registration. We see later. Antonio Moles, about the torque ripple. Okay, this is about which is the difference between the two switching case. The torque ripple is just induced. Let's say the difference between the minimum and maximum current I provide you is always the same in both the cases. Okay, the difference is in the frequency of the ripple. Okay, the frequency of the ripple has some impact depending on the inertia of the system. Okay, for example, if you have a ripple which has a larger frequency, okay, in that situation the ripple torque can be less with respect to the situation in which your ripple current has a say frequency which is lower. So in that case, if you want to consider which is the minor impact on the ripple torque, this is due to the less frequency ripple. Okay, because if you have, let's say, a frequency which is very large, typically this is not exactly followed by the torque ripple. Okay, you have the dynamics of the mechanical system is, let's say, slower, and it is, let's say, it cannot follow exactly a very large frequency variation of the current. So it's best you have a large frequency if you want in this case. But anyway, we can see after the break a solution to avoid the ripple in the torque. Okay, which is another second. Okay, let's have a break. 10 minutes from now. Okay. Okay, just to conclude, to say provide, let's say, a little bit more detailed answer to the question of the student Antonio Moles about the torque ripple. I'm just saying, and then maybe is better to say have a little plot here of the current through the phase. If you have a current that has, let's say, this behavior, okay, and so this is a very large frequency in the phase here, which you can have the, let's say, on phase, or the phase is energized with respect to this situation. For example, something like this. What happens that if you have a variation of the current, say that include a time interval so large, okay, this can trigger more easily the variation of the torque with respect to this situation, because especially if you have a large inertia, okay, maybe the motor does not, let's say, recognize that there is a variation of the current due to the fact that there is a large inertia and that the frequency of variation of the current is very fast. Okay, here even if you have the same, say, band, say, hysteresis level, since the frequency is, let's say, very small, in that case, you can have a little bit, say, more problems with the same inertia of the motor, because these, let's say, very slow variation can trigger the variation of the torque, just to summarize up. Then also depends on the torque, especially on the motor, etc. Let's to continue what we are discussing. So the chopper driver, let me just to redraw the chopper circuit. Here we have the voltage V provided from the external side. Again, let's say put here a switch, the phase, and the bottom switch. Okay, LA, RA. This is TA plus, TB minus. This is the diode DB plus, and this is the diode DA minus. Okay, this is our chopper drive. Just a few words about how to choose the switches in the circuit. What happens, for example, when this switch can be MOSFET or IGBTs. When you want to buy a switch for your application, you have always to consider that you should define which is the maximum current that flow to them, for example. Or sometimes you can also define which is the Aron resistance, okay, which is the resistance in terms, especially for MOSFET, that you may have when the switch is closed. And then if you also design the which is the breakdown voltage, okay, because in the catalog datasheet you can find switches in terms of the maximum admissible voltage when the switch is open, so the breakdown voltage, and the current flowing to them, and also the Aron resistance, for example. So which is the maximum current that can flow through these switches? The maximum current is, let's say, when since they are connected in this way and they are, say, conducting the phase current IA. So for the switch, maximum current through TA plus and TB minus is, let's say, what I call I final in my example, especially in referring to that example, it's 10 amp, for example, okay? Which is the maximum breakdown voltage, which is the sorry, the maximum breakdown voltage of the device. Consider, for example, the situation in which you have TA plus, which is off, which is, for example, this situation here. Okay, so this one, which is the voltage that you can have in the open switch. Is exactly, since in that situation you can have this diode which is conducting, okay. The voltage here is V plus VF. So the breakdown voltage should be higher than V plus VF. VF typically is, let's say, negligible with respect to V, so this is higher than V. This happens also for the in the situation which you have, let's say, this closed and this switch open. Okay, the voltage here is exactly V plus the voltage drop across dB plus, which is on. Okay, so this is for, say, choosing your transistor. This transistor here, TB minus, is a low side transistor. Low side means that it has one terminal, say for MOSFET this is the source, which is connected directly to the reference node. Low side transistors are easier to be driven with respect to the high side transistor. And an example of high side transistor is this one. So in that specific case, you have let's say two different drivers needed to provide the voltage required for commanding the status of the transistor. Typically, high-side transistors are a little bit complicated, more complicated. For sure, they are more expensive than driver for low-side transistor. But in that case, you have both high-side and low-side transistor. Using these strategies, the torque versus the frequency is, let's say, something like this. So it's something that can be, let's say, employed for obtaining a very large torque, even for large pulse per second. Typically, this kind of chopped driver is integrated, so you can find in, say, a single chip that you can use for your unipolar stepper motor. I said before that for bipolar wiring of stepper motors, so all that cases in which the rotation of the driver is obtained by making the current through the phase to be bidirectional, say not just flowing from the node A to node B, but also in the opposite case, you need a bidirectional driver. Okay, this driver is a two-quadrant, which is unidirectional in current and reversible in voltage. When we learn about how to build a bidirectional driver, bidirectional converter, then in that situation I'll also give you indicate to you, provide you information about driver for bipolar stepper motor. Okay, something that we already still don't know up to now. I said before that there is a drawback in this configuration, which is the ripple in the current. Okay, this can be a drawback or no, depending on the inertia of the motor and the tolerance, etc. And typical solution is to generate, let's say, to use another circuit to, if you want to be sure that no torque ripple is generated. Okay, just a few another, say, words for concluding this discussion that comes in mind up to now is about the sensor current. Okay, you have a current here, so your circuit, a current sensor that measures this current here and provides this information inside a controller. Okay, inside this controller, possibly there is a comparator that compares the current with a specific threshold, maybe two thresholds. Okay, one for the minimum current, another one for the other current, and this controller provides the function for, let's say, here for driving the status of the two switches. Okay, so in order to get exactly to pass through the sequence I shown you before. Okay, if the current is reaching the I final current, so the 10 amp in my example, it means that I have to open the TA plus in this case. Okay, if the current reaches the minimum 5 amp current, which is admissible for that application, then I have to go is I have to close the switch TA plus. Okay, so the action basically is for this transistor here, this as example, or the opposite if you choose the opposite say combination of the switches. Okay, so this is always, let's say, what you can find in integrated controller. So just to say complete this discussion by illustrating the behavior of a circuit that totally eliminate the current ripple. The kind of control that is indicated here is can be a name which is hysteretic control action, okay, because it say change the status of the switch depending if you overcome or then you are below a specific threshold. Okay, these circuits that eliminate the ripple is somewhat similar to say what we discussed up to now, because that's basically the same topology. There is just one big difference. Okay, so TA plus TB minus RA are the modeling of the phase. Freewheeling diode DB plus. Here we have the diode. Let me call D A minus as before, but now the anode of this diode is not connected to the reference node of the circuit, it's connected to another voltage source. Let me call this V2, okay? Where V1, sorry, V is larger than V2. Let me just say discuss the operation of the circuits based on what we already know from the previous chopper circuit. Okay, suppose that you want to turn on the circuits. If you want to turn on the circuits, TA plus, TB minus, both on. Okay, exactly as in the previous situation. What happens when both these transistors are closed? The circuit basically is this one. So you can see here diode DB plus is off, is reverse biased by the voltage V. What about DA minus? I said that, as you can see, the anode here of this diode DA minus is at voltage V2, but the cathode is at the voltage V. But V, by our previous definition, is larger than V2, so also DA minus is off. So the result of this action is that nothing changed with respect to the previous case. Okay, the equivalent circuit is again basically this one, in which the voltage VA is plus V, and so we have the standard variation of the current through the phase. TA plus TB minus on. This is the current I. Okay, so now what happens? Of course, the current goes up when a specific current sensor recognizes that we reached exactly the nominal current I want to say the stepper motor as in its phase. I have to change this configuration. Okay, so this phase ends when I reach the nominal phase current. Then suppose that I have, for example, in this case, this transistor to be off, okay, and TA plus again to be on. What happens? In that specific situation, basically the current flow into the phase here, the phase that has this current IA, is interrupted. And so you need to consider this other situation, sorry, because of course this is the situation I want to consider. TA plus off and TB minus. Okay, so I'm interrupting the current. So what happens here? That the current needs to be recirculating. Okay, and using these strategies, this combination of the switch, what happens is that the current cannot flow, let's say, in this circuit here with the diode DB, only because this transistor is open, and so the current flows here, making TA minus to be on. So the second phase is that when TA plus is off, TB minus is on, TA minus becomes on for, say, freewheeling this current. Now, the idea that makes possible to eliminate totally the ripple current is to have the nominal current, the current that I indicated as I here, to be exactly V2 over array. If the nominal current is exactly V2 over array, what happens? When you, say, open TA plus and close, say, TB minus, as you can see that the initial current that you can have here, which is I, because at the beginning of this stage, the current is already I, is the same of the current you can have at infinite time. So when you say have no more the action of the inductor, so in a stationary condition, exactly the same. So you have a situation which has no transient at all. Okay, so the current here has no transient at all, and so the current remains constant. So this situation can hold for all the time needed to have, let's say, the current flow into the phase. So this is TA plus off and TB minus on. Of course, when you need to, say, turn off the phase, you could, say, apply both switches to be off. Here, TA plus off, TB minus off. When the switch are both off, what happens? Situation this one. Now the current has only one possible path. And the path is this one. Okay, so again, let me call A and B at the terminal ends of the phase. You are in the situation in which at the node A you have, let's say, V2, at the node A have V, and so in that situation, for TA plus and TB minus both off, the voltage across the phase, let me call VA is V2 minus V, which is negative because V is larger than V2. Okay. If you want, the drawback here is that you do not have the turn off. At the turn off, you don't have the same voltage, negative voltage, that you can have in the previous circuits. In the previous circuits, you just have negative V. Okay, now the negative voltage here is somewhat less than before because you have also the presence of the voltage V2. So this means that in this case, this transient at the turn off is a little bit longer than before. Okay, then especially the turn on and the turn off are not symmetrical. While in the previous situation, with the ripple in the current, the turn on and the turn off are totally symmetric because they have the same slope, which is V over L. Now we have two different slopes. Okay, at the turn on, the slopes here is V over LA. At the turn off, you have V2 minus V over L, which is, say, less than before. So this means that turn off is a little bit longer. Okay. This is the usual drawbacks that you can find that kind of the circuit in where for solving some problems sometimes some other situations some other issues can arise. Okay, in that situation you have no more ripple in the current here because this current is exactly V2 over R A, but then say you have to wait for a larger turn off time. Okay, so that means that your torque is not so high, increasing the frequency of the rotation of your stepper motor. Okay, so this is an alternative solution that you can use. Of course, this circuit is complicated because you have to insert here another voltage, another supply here. Okay, this increases the circuit. So this is another drawback you have in this case. You have questions, problems, whatever, curiosity? I don't know. Okay, I think that this part ends the stepper motor description. Okay, about the driver. I said before that in order to have a driver for bidirectional stepper motor, you have to use something that we already have to introduce. So when there is the possibility to say comment on the use of bidirectional converter for stepper motor, I will give you some hints. Okay, so let's change the topic. Okay, I'm describing something that goes toward the description of the more general converter that are the 4-quadrant bidirectional converter. And in order to describe these circuits, let me just introduce, very simple steps. Okay, the first one is can be discussed under the generic title, let's say, switching operation and circuital topologies. So I'm referring now at the slides that are indicated as number 5. Okay, so you can find my discussion is in number 5. If I remember, I'll be directional converter. Okay. Let me just discuss some specific properties of switches when they are operated, let's say, in what is called forced commutation or hard commutation. And in order to understand what I'm going to describe, consider a very simple example. I have a circuit in which the switch S connects a battery, a power supply, with a load. Okay, so this is the case of a ohmic load. The switch S is, as usual, characterized by a voltage V across it and a current I that flow through it. Okay. The current I also flow here, so the voltage here is the voltage across the resistor, Ri. So we can say that the voltage V across the switch is simply given by E minus VR, so E minus Re. Let me put this very simple expression into a plane in which I have the characteristic of the switch, the voltage V across the switch and the current E flowing through the switch. Okay, I can also put this characteristic on this plane because this characteristic has the following behavior. When the current is null, the voltage V is exactly E. When the voltage is null, the current is E over R. Okay, this is what is also called the load line. Okay, describing all the operating point of the switch in this plane. Now, suppose that the switch is not an ideal switch. Okay, this is just a very, say, not an ideal switch, but a simplified hypothesis. Okay, so I am considering that the switch can be described as a very small resistance when it is on, so when it is, say, like a closed switch, and a very large resistance when the switch is open, when it is off. Okay, so this is my model. So that means that the characteristic of the switch in this plane, according to this model of the switch, are simply given by these two segments. Okay, this is the characteristic for a very large resistance, and this is the characteristic for a very small resistance, R small. Okay, so if you want, this is the situation when the switch is, that's a characteristic of the off switch, and this is the characteristic of the on switch. Of course, the intersection between the load line describes the circuit which is connected to the switch. Okay, so this is the circuit connected to S, while the switch is described by the orange segments. The intersection that you have between the characteristic of the switch and the circuit which is connected to the switch provides you the operating point. Okay, so it means that when the switch is off, it operates here. It means that it has a voltage across it which is a little bit lower than the supply voltage E, and it is a current which is very small. Now it's exaggerated because typically it is an open circuit. And so this is the off operating point, and this is the on switch point, the on operating point, so when the switch is closed, in which it has a very small voltage and a current which is basically E over R. Okay. What happens that when you want to turn on your switch, you go in this direction. When you want to go turn off, you have to, say, provide the opposite direction across the load line. Okay, so the characteristic of the switch goes from the off to the on point and vice versa, and intermediate operating points always lie in on the load line. Okay, of course, the operating point in between are very fast. Okay, static situations when you have off and on situation. Let me just spend a few words about the power of this circuit. The power dissipated by the switch. The power dissipated by the switch is the voltage multiplied by the current through the switch. Okay, the voltage is E minus VR. Okay, divided. Multiplied VR over R. Let me put it this way. So this is E VR over R minus VR squared over R. Okay, this is the power dissipated by the switch. Where you have the maximum possible switch, you have to take the derivative with respect to the voltage VR, because we are, say, interested in understanding for which VR we have the maximum power dissipated by the switch, to put this 0, and then you get E over R minus 2 VR over R equal to 0. And so you get that VR E divided by 2. Okay, so for that specific voltage, VR, the voltage V is E minus VR, so it is E divided by 2. So when the voltage across the switch is V divided by 2, so it is here, you have the maximum possible power. It happens when you transitate, when the switch transitates from the on-off or off-on situation. Okay, the power as a, say, since is the product of the voltage and the current in the plane VI is a say as a parabola expression like here. This is the point having the maximum possible power, and of course you get the, say, situation which is tangent exactly at the point in which V is equal to E divided by 2. Okay, so this happens that when you close the switch and open the switch, it happens and during this transition, exactly at half the dynamic of the switch voltage, you meet power curves that gives you the maximum possible power. Okay, this is just something that we can use for reference and for comparing other more interesting situations. Let me just introduce the situation which you have inductive ohmic load. Okay, so no more a resistive load, but then we have the switch that connects the power supply here with a load which includes an inductance L and a resistance R. Vi, this is the switch S. VL, VR, so the voltage V is E minus VL minus VR, so it is E minus L the I on the T minus R multiplied I. Okay, so again, consider what happens in the IV plane of the switch. Let me put the characteristic here of the switch that are basically very close to the axis. Okay, here. So for the open switch and for the closed switch here. And see what happens, for example, for the, let me start with the turn on. Turn on means that I'm closing the switch, okay? So I'm closing the switch, and if I close the switch, what happens is that the current increases. And so the I on the T is positive, okay? Because when I close the switch, the current is 0, and then from that point, the current becomes positive. So the I on the T positive means that if you look at this equation here, means that this term here is positive, and so you are subtracting a term which is positive, meaning that the voltage V should be less than E minus Ri. Okay? The amount by which this voltage is less than E minus Ri is the product L multiplied the I on the T. Remember that V equal to E minus Ri is the load line. This one, which has a graphical representation by the blue curve in this slide here. So let me put here the load line. That has always E over R and E as intersection with the main axis here, describing so V equal to E minus Ri. Okay. Now, these equations simply states that all the operating point of the switch at the turn on lies on a region of the plane that are inside, that are, say, inside this lower triangle, so in a region lower than the load line. For example, this is the on and this is the off point. I'm talking about the turn on. So one possible trajectory of the operating points at the turn on could be something like this. Okay, so that means that when you turn on your switch, the voltage across it reduces, and simultaneously the current is increasing. Okay, and so, for example, so all the trajectory you can have for your turn on this kind of inductive ohmic load are, say, under the load line for resistive load. For example, this happens for a specific di on the T. If you increase the di on the T, then the curve should be something like this. Okay, so this happens for the I on the T that are increasing. Okay, if you have the I on the T, which is, let's say, ideally infinite, then the trajectory will be, let's say, adjacent to this axis here, orange axis. Okay, before the current, the voltage instantaneously goes to zero, and then the current, let's say, instantaneously becomes the final current. Okay, so but all the trajectory involves, let's say, this part of the plane. What happens at the turn off? At the turn off, you are, say, interrupting the current, so you are forcing the current to decrease. So that means that you have the I on the T, which is negative. Okay, and so if the I on the T is negative, this contribution now, which is subtracted, becomes positive, and so V should be larger than E minus Ri. So in that situation, all the operating point at the turn off this inductive ohmic load are in the region of the IV plane that are higher than the load line. So are in this region here. For example, if you want to consider the turn off, you can have something like this. Okay, the current decreases and simultaneously the voltage increases. Okay, if you have variation that are very fast, it means that you can have, let's say, something which is again something like this. Say. My drawing is very bad, but I hope that you understand the situation. Now, what happens in terms of dissipated power? Remember what I said before about the power dissipated by the switch in this circuit, okay? You have this kind of hyperbola, which is the resistance, the power dissipated by the switch, okay, the product of the voltage and the current. If you increase the power, okay, this hyperbola means that is something like this. So large power means that this curve, there is a family of curves that are parameterized by the level of the power which is dissipated, and then you can get something like this. So you can see immediately that in the case of inductive ohmic load, when you operate the switch at the turn on, so in the region which is the blue one, then all the operating points of the switch meet the power curves, let's say, that leads to a very small amount of dissipated power. While the opposite happens when you turn off your switch, because when you turn off the switch, the situation is now in the higher part, okay, of the graph, in which there are the hyperbola of the power that are parameterized by the highest level of the power. Okay, so we can say that the turn off is dissipative for inductive ohmic load. So when you interrupt the current by a switch which is operated exactly in the way I show you in this page, that situation leads to the very large dissipation of the power. And faster is the transition, is the turn-off transition, faster, let's say higher, will be the dissipated power, up to the point that the switch cannot be, say, more useful because of physical damages. If you think about a similar situation that we met in the previous analysis of a stepper motor, is a situation in an L over R driver, okay, when I say turn off a phase, say I have to open the MOSFET, I open the switch, and that situation immediately the voltage across the switch reaches the maximum possible level, which is the breakdown voltage, okay? That situation is very dangerous because if you are not able to control the energy involved in that situation, you get permanent failures of the MOSFET. You have to replace it, okay? And the same situation described in this way is a more, say, if you were, intuitive way, okay? you have a sort of not compatibility of the action of the switch with the turn-off action in this inductive ohmic load connection. This is due to the fact that you are basically interrupting a current which is not null flowing through the inductor. Okay, anytime you are interrupting a not null current flowing through the inductor, then something dangerous leading to very large power dissipated happens. Okay, so this situation, the turn-off situation, is not compatible. Of course, if you are very lucky, maybe you are acting your switch, you are opening your switch when the current in the inductor is null. In that situation, nothing happens. When you are, say, changing, when you are interrupting, we are turn off a circuit in which you have an ohmic inductive load, and in that situation the current is null, then in practice you are not interrupting nothing because the current is already null. In that situation, you are not exciting any dissipated power. Okay, but this is not the situation that I want to discuss here. The discussion is about what is called the forced commutation. Or sometimes the hard switching. So that means that I want to open the switch anytime I need for it to be open, or close it if you want. Okay. The situation that I described you before, so the situation in which having the same circuits I show you in this page, you open the switch exactly at the time instant which the current in the inductor is null, is called zero current switching action. Okay, zero current switching for that ohmic load circuit leads to no dissipated power. In forced commutation, there is no, let's say, this kind of sensitivity. Okay, sensitivity. I don't look at the correct time instant that leads to the minimum amount of power dissipated. Okay, so there is a total different way to operate the switch. Okay, this is typical for resonant circuits. The zero current switch. Resonant circuits are a totally different class of power converter. Okay, that leads to very small dissipated power during the switching action. Okay, interesting, but in practice I have no time to talk of this class of converter. This is for the ohmic inductive load. Consider what happens for the ohmic capacitive load. Again, we have a voltage source that is connected through a switch S through a ohmic capacitive load. Capacitive load. C and R. This is VC. This is the current, let me call IC, IR. So now look at the node, then you can see that I is IR plus IC. IR is the same as of VC over R, while IC is given by this expression. So VC is the voltage across this branch, okay? And so you can express VC in terms of the voltage V of the switch. So this is E minus V over R plus C the E minus V the T. And so finally we have that this is E minus V over R plus practice we have a minus C the V over the T, since E is constant, so we can take the time derivatives, you get 0. Okay, so now as before, let's plot the on the IV plane on the switch of the switch characteristic, the, let's say, switch model, large and resistance, low resistance. Plot the load lines for the resistive load, which is E over R intersection and E intersection. Okay, so this is E minus Ri curve, the load line. And so start considering what happens during the turn off. During the turn off, it means that I'm opening the switch, okay? If I open the switch, what happens to the voltage across the switch? So what happens to the V over the T? During turn on, the switch was closed, so the voltage V across the switch is 0. At the turn off, the voltage V increases, so it becomes positive. And when you get positive, the V on the T means that this contribution here in the current I is really subtracted from the current I. Okay, so on the current I becomes less than E minus V over R. Okay, so what does it mean, this contribution? You can express in terms of the load line, meaning that you have that all the operating point at the turn off lies in the lower part of this graph, the part below the load line. Okay, you are at the turn off, so for example, you have something like this. Of course, faster is this turn off, and larger will be the terms the V on the T. So you can have something like this. Ideally, when you have infinite or instantaneous turn off, you get, say, that the axes are, say, the possible curves. Here you can see that all the operating points interest a region of the space in which the power which is dissipated by the switch is, let's say, low. So in that situation, this transition is not something which is we can call dissipative. Okay, it's not a problem. It's not an issue. What happens for the turn on? At the turn on, basically, we close the switch. Okay, so from a situation in which the voltage V across the switch S is, let's say, positive, we are now forcing the voltage to go to 0. Okay, so the V on the T decreases. And if you put negative sign in front of the V on the T, what happens that the current I is larger than E minus V over R. And so in that situation, all our, say, operating points at the turn on are in this region here. So in the region in which you met for very large power dissipation. Okay, so this is dissipative. If you want, this circuit is the, let's say, opposite circuit for the ohmic inductive load, because the situation is reversed. What is dissipative for the, say, inductive load circuit is not dissipative for the ohmic capacitive load, and vice versa. What we can consider here is that having a switch that is acted in what is called the forced commutation, so switching without any regards the value of the current or the voltage across it, leads to not compatibility of one of the two actions, turn on or turn off, depending on the characteristic of the load. If the load is, say, capacitive load, then the turn on is very dissipative, leads to possibly permanent damages and failures of your switch. In the case your load is inductive, mainly inductive, what happens that the turn off is a dissipative action, is not compatible with the first turn off of your switch, leading to possibly permanent damages. Okay, so one of the two actions, depending on the load, is always not compatible. Okay, so this is a situation that we have to face off. Even here, if you are very lucky, maybe you are closing the switch exactly in the why the turn on here is dissipative. The situation is exactly the same situation that we met for the inductive. Okay, with the inductance, the turn off is dissipative because you are forcing to zero a current that flows through the inductors, and the current was not zero. In that situation, if you are very lucky, and when you turn off the current, when the current inductor is already zero, then nothing happens. Here, the situation is the same. If you close the switch, you are forcing the voltage VC across the capacitor to be the same of the voltage E. Typically, these two voltages are not the same, and so this leads to, say, problems. But if you are very lucky, then you are closing the switch when the voltage VC is the same of E. In that situation, nothing happened, then the more dissipative. This situation leads to what is called the zero voltage switch action. That again is a typical situation for resonant converter that leads to very low power dissipated during transition. Okay, but this is not the case I say the possibility to discuss in this course. In this course, we are just focusing on the hard commutation, hard switching, and in that situation, there is no compatibility in one of the two possible actions: turn off for the inductor load and turn on for the capacitive load. Okay, so we have to discuss a possible solution, so a possible circuit that make possible a non-dissipative action both for turn on and turn off for capacitance load and inductive load. Okay, this is my goal. I want to discuss which is the solution for this forced commutation problems, which is the non-compatibility of the switching action. So in order to see what happens, let's start with the inductive ohmic load. Okay, suppose that you have the inductive ohmic load, and we want to solve the problems of the dissipative turn off. Okay, so suppose that you have the same voltage source here, and then suppose that you have your switch, and here you have your, let's say, load, L, R, etc. This situation with forced commutation leads always to dissipative turn off. Okay? So we have to consider a different topology. We have to modify a little bit this circuit in order to provide compatibility between the force or the hard commutation of the switch and the load, inductive load in this case. Possible solution is to complicate a little bit the configuration of the switch. So not just one switch is enough, we have to add another switch, okay? The problem is at the turn off. So when I open the switch, I'm interrupting the current flowing here. Okay, so I need another switch placed somewhere in this circuit that make possible for the current through the switch through the inductor to continue to circulate. Okay, this is something that you already saw in this course. Suppose that I have another switch here. Okay, and also suppose that this switch acts in this way. Let me call this switch switch A plus, and this is the switch A minus. Okay. Let me just start with the turn on, which is the non-dissipative situation. Okay, so I want to solve the turn off situation, but I don't want to to put something bad in the turn on situation, which was already non-dissipative. At the turn on, I have to close the switch. Suppose that when I close the switch, I open this other one. Okay, so switch A plus is on, but simultaneously switch A minus becomes off. The circuit is exactly the same circuit I analyzed before, because the switch switch A minus is not present. Okay, so I get the same consideration I had before. The turn on is not affected by the presence of the switch A minus. But at the turn off, I want the opposite behavior. I want to open switch A plus, so to make it off, and I want to close the switch A minus. In that situation, the current flowing through the inductor is no more interrupted, because the circuit now is something like this, and the current flow in this mesh. So the current continues to recirculate. What about the voltage and the current in the switch? The voltage across the switch becomes E. Okay, so it is a safe level. Is not, you have no over voltages, and so it happens to be not a problem. Okay, and the current from the initial level, which is IL, goes towards zero. Okay, without too much delays. Is the current that almost instantaneously becomes null. So the voltage V is clamped to the external supply source E, and so this is something that do not lead to any over voltage. Compare this situation to the situation I have here at the turn off. At the turn off, I have operating points that occupy the part that is in over the load lines. Okay, and as you can see here, there are some specific operating points. Maybe I don't fully complete this graph here, that leads to voltage that are larger than E. Okay, so it means that if the switch is not protected from over voltages, then you can have problems. Okay, the situation here is always indicated dissipative, because the dissipation in that region is larger. Okay, you have get over voltages. Okay, and this is basically a problem. But here there is no over voltage because the voltage is clamped. Okay, this diode, this switch, which is switch A minus, is also called the free wheel switch. Okay, it provides a path for the current flowing through the inductor, which is not, let's say, need to be interrupted. See that these two switches act in a complementary way. A complementary way means that one switch is on, the other one is off, and the vice versa is also true. And so if you want, this combination acts in the same way of a bipositional switch. Let me just redraw the circuits to make evident this behavior. Okay, I have this bipositional switch here, and then I have the ohmic load. Okay, so this switch is connected at the node 1 at the turn on, and is connected to the node 2 at turn off. Okay? The same situation can be described in terms of the presence of a bipositional switch. This terminal here is called the common terminal. As you can see, this common terminal is connected to the inductor. Okay, while the two nodes 1 or 2 are, say, facing the external battery E. Okay, so this happens for the inductive ohmic load. How can you, let's say, force the commutation of the switch? The commutation of the switch can be forced by using a command signal. Okay, the command signal is provided by the external side. Let me call, we also meet this say combination previously in this course. Okay, so nothing new is here. Just try to formalize in a large way or something that you already know. Q is the unitary switching function. That can be 0. It means that switch A plus is on, or if you want to describe in terms of bipositional switch connected to node 1, or can be 1, logical level 1, so high logic level, when switch A minus is on, so connected to node 2. So by using a low power logic level as unitary switching function, I command the position of the switch, commanding what is called the hard switching of this switch. Of course, if you are looking at this combination, the unitary switching function directly command the position of the switch A plus, and in order to derive a function for commanding the switch A minus, you have to, let's say, have the logical knot of the function Q. Okay, so Q is 1 means that switch A plus is on, 0 switch A plus is off. Not Q, which is 1 minus Q, will be 1, meaning that switch A minus is on, or 0, switch A minus is off. Okay, so let's stop here. Tomorrow we continue with the capacitive ohmic load to understand which is the best topology for driving, for avoiding the turn-on dissipation in case of capacitive load. Okay. Have you question about this, what I said up to now? No questions? Okay, if you have no questions, I can interrupt here. Okay, I have a question. Emanuele Elia asks, should we introduce a resistance? Where? Where do you want to introduce the resistance?
Can I use my microphone?
Yes, sure.
Okay, I think it's better to introduce.
So
Okay,
I cannot hear you very well.
It's better now.
Yes, more or less. Try to ask the word.
I'm referring to the circuit before this one, this last one.
This one in
Yeah, when
okay,
we had the two switches.
the previous one.
Yes, the previous.
Okay.
In this case, maybe a resistor in the freewheeling circuit.
So you want to put a resistor here in place of the switch A minus?
No, in series.
And why?
Just to avoid that we have overcurrent when closing the switch on the freewheeling.
So if I understand what you are saying, you said that if I put a resistor here, right? When
Yeah.
I close the switch, what happens? When you close the switch, there is a current flowing, which is exactly the same current as before. There is
Yes, but I thought that since the switches doesn't don't act instantaneously, so we have a short period of time in which the switches can be close together. So having a large amount of current from the source.
Okay, you are introducing something which is not ideal in this this discussion. Okay.
Yes, exactly.
Yeah, of course, I'm just referring to the situation in which the action is perfect. That means that you have no situation in which both switches are simultaneously on. Okay. Of course, if you have this say drawback, what does it mean? That when this, if say, unfortunately, switch A plus and switch A minus are simultaneously on, even for a very short period, then you are shorting your supply, okay, because both switches are closed here, and then a very large current flow through this mesh, possibly inducing permanent failures and malfunction. This is your discussion, right?
Yes.
Okay. In that situation, the presence of a resistor here, but you can put this resistor here, or maybe you can put a resistor here, somewhere in the same mesh. No?
I think it's better in the freewheeling mesh because on the source we also dissipate during the turn-on phase. That is what we
Okay,
want.
but at this level of the discussion, exactly, at this level of the discussion, I can see that your idea can be, say, good, but we'll see later that there will be other solutions for this possible problem you can have, okay, which does not involve the presence of resistors. Okay, Marco Simonetti asked, for example, there will be the body diode, okay, and of course, when you use MOSFETs or IGBTs, you can have the body diode that can help in managing this kind of problems, okay, the cross conduction. Another solution for this problem is what is called the dead time. So avoiding the simultaneous conduction of the two transistors. Okay, and this typically is always done in practical converters. Okay, it is specifically avoided this case. While in your solution, which is the resistance R, say here, is inserted when you have this cross conduction, okay, and I can say agree with you that putting a resistor there can reducing the current, okay, that's sure, but the best solution is to avoid cross conduction, and this can be done. This is always done by inserting a very small dead time, which is a time interval in which both diodes are off. And in that specific case, both the diodes provides conduction, free will conduction of the inductor current. Okay, so but we are putting too much, say, topics in this to answer your question. Okay, I hope that, of course, your solution can be good if you are, say, have this cross conduction. I prefer to avoid the presence of resistors because they dissipate power. Okay, so for that reason, other solutions can be implemented. Okay, thank you. Anyway, thank you for your questions. Is correct at this level of the explanation. Okay, guys, we can stop here. We can see tomorrow morning 10 to continue this discussion. Okay, see you. Bye.